I will begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. And Lord, thank you for these students. Just ask you to bless this class. Help us to just understand a little bit more, again, about your creation this day, Lord. In your name I pray. Amen. All right, so today, integration. How and why to integrate. So I want to describe to you integration for functions of several variables. All right. Now, our starting point is just going to be to look at a problem that you might find interesting. And that's this. So to keep things relatively simple, I'll picture it something like this. And so here's my z, and here's x, here's y, all right? And I'm looking at a graph, right? I'm looking at a graph z equals to f of xy, right? And what I want to try to figure out, and I kept it relatively simple, to start with at least, we'll look at a rectangular domain for the integration region. And so we'll say, you know, let's see here. Actually, I won't assume that it goes back. I'm going to just change it up just ever so slightly. I'm going to kind of like go like this. In the sense that, that was dumb. Didn't change my picture at all. But what I was trying to get at is I'm looking at that as being the image from A to B, like that, and then over here from, say, C to D. So like A, well, here's my futile attempt at a picture of the domain down here, A cross B, A comma B, Cartesian product with C comma D. In other words, this is the set x comma y such that x is stuck between A and B, and y is stuck between C and D. All right, so I want to describe how to calculate basically the volume that's stuck between. All right, I'm just going to have to modify my picture to suit my purposes. Okay, so apparently I was looking at this part of the thing. And so here, this is the larger, it's the extension of the graph past the point I don't care about, yeah? This is the z-axis, which seems to have moved. All right. Anyway, you get the idea. Well, maybe you don't get the idea. I'm foolishly attempting to try to illustrate this sort of, let me try again over here. So, I'm looking at some sort of rectangular domain, and then I'm looking at the graph that sits over it. If you project the graph down into the xy plane, you get this A comma B cross C cross D, okay? The question then is, what's the volume? What would be the volume? How would we calculate the volume of such a region, right, such a shape? And so the sort of answer that most people would probably give if they've had Calculus 1 is chop it up into pieces, right? Chop it up into pieces. And so what you could think about doing is just, basically making little boxes down here, right? And thinking about the skyscraper that kind of fits over that box, right? My picture gets very, very cluttered very, very fast. So back here, you could think about another box over here, right? And so for each one of these boxes in the domain, you got some like skyscraper over it, right? And you could calculate the volume of the skyscraper, what would the volume of these, I keep calling them skyscrapers for lack of imagination, what would the volume be for the ijth one? If this point, so we could pick a point here, say that the point on the top is x sub I star y sub j star f of x sub I star y sub j star. So I'm saying that starred point is the one we use to fix the height of the skyscraper. All right. So if that's the case, what's the volume of the skyscraper going to be? It's going to be the change in x times the change in y times the function evaluated at that sample point. Right? So here I'm assuming that the change in x is this, and the change in y would be that. And to keep things simple, we could think about the change in x and the change in y being the same, throughout the grid, just to keep the approximation most simple to discuss. If you wanted to, you could use a different grid size in the x and versus the y, right? Yeah, let's do that. What if we let delta x and delta y have kind of like they let's suppose that they're uniform across the division, but they're not, quite the same. Let me just focus on the grid here for a second. So I'm just going to draw y this way and x this way. So we've got our A, we've got B, we've got C, we've got D. Here's the domain that we're integrating over, right? And so I might call this point right here x sub naught, y sub naught, right? And I could call this point up here, say x sub m, as in mommy, and y sub n, as in nenu nenu. And I could think about, n divisions here. And I could think about m subdivisions here, divisions, I guess. Or I guess I should probably say subdivisions. That's usually what we say. So if I did that, if I chop like that, what's this would be my delta x. What would delta x be equal to? X sub m minus x naught over m is true, but I was looking for b minus a over what? M, right? And what would the delta y be? Yeah, d minus c over n. And to be more explicit, we could say x sub I was equal to x sub naught plus I times delta x, right? And we could say y sub j is equal to y sub naught plus j times delta y. And that's how we would explicitly build this grid of points, all right? We could explicitly build this grid of points, just like we subdivide, just like we subdivide. These are supposed to be equal divisions for the sake of my setup. The proper logical definition of the integral does not assume equally sized divisions. Like the full Riemann integral allows the subdivisions to be different sizes as variably as you like. But this is not an analysis course, so I don't much care. Let's see here. So if we focus in our attention, say, on that being the ijth box, then I'm saying that x sub I star y sub j star is in there. So I'm just saying the sample points have to be points in these boxes. Like, it could be here, it could be here, 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 here. Could you guys think of any rule to pick the sample point? No. We want one sample point per box. That will fix the height of the skyscraper over the domain to set up our approximation for the volume under the curve, under the graph. All right, so what's the approximation? volume, rather, is approximately what? The sum, I equals 1 to m, sum j equals 1 to n, right, of f of x sub I star comma y sub j star delta x delta y. I mean, that's an approximation to the volume. It's obviously not the volume, right? I mean, because if we take a finite grid, we're overestimating and underestimating the actual volume in kind of a haphazard way. To go back to my question that I posed to you guys, one way you could pick these points would just be to pick like the middle point of each grid, right? For like the central point of each thing. You could pick the lower left-hand corner. You could pick the upper right-hand corner. You know, pick a specific corner on each box. You could do that. I mean, there's a ton of different, in Calculus 1 or 2, you probably studied the left, right, and midpoint rules, right? If you think about this, there's like a, I mean, you think about the choices here, you could make all kinds of different choices. But the theory here says that it doesn't matter what choice you make, the thing I'm about to write down is uniquely defined. And to be more fussy, it should be between the upper and lower limiting sums, blah, 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 but you know, that doesn't matter to us too much. This volume, we write a symbol. It's defined to be the double integral over, and I need to give this thing a name. We're going to call this region R. All right, so the double integral over the region R, all right, of f of x comma y dA is by definition, so what I'm saying is that this symbol denotes the signed volume under the graph of R. Graph of f restricted to R, really. And it's going to be the limit as m goes to infinity, the limit as n goes to infinity of the sum I equals 1 to m, sum j equals 1 to n of f of x sub I star, y sub j star, delta x delta y. So this is just the double Riemann sum. Yeah? And I hope you understand from this discussion why that should calculate the signed volume under a graph. Does that make sense to you? Why it should do that? I mean, here's how I think of it infinitesimally. So this is just a formal slogan, if you like, but I think it's a useful one. Infinitesimally, f dA is equal to dV. That's the little bit of volume over dA for z. You know, 0 less than or equal to z less than or equal to f at the point. dA is at the point x comma y. And you just add those up. That gives you the whole volume, and that's the double integral. Special case. What if we just do the double integral? Special case, right? Integral over R dA, what's that equal to? If you take a graph of height 1 and you calculate the volume under that graph as it sits over some region, what have you actually calculated? I tell you, a box of height 1 has volume 10. What's the area of its cross-section? It's 10. If there's any justice, this should be the area of R, right? Yeah. Now, technically speaking, this is what you'd call the signed volume, right? Why is that? Signed volume bounded between z equals to f of xy and z equal to 0. So basically, volume that's below the xy axis counts as negative in this setup, right? Volume above the xy axis counts as positive. How would we define a triple integral? How would you define a triple integral? Well, if we had a region, say B, some subset of R3, right? For example, B could be A comma B cross C comma D cross, I don't know, Pac-Man comma Ghost. So I'm talking about some kind of cube, right? What's the back point there? A comma C comma Pac-Man. What's the point that's the most out there? That would be B comma D comma Ghost. I know you guys are not used to this Cartesian product notation. That's why I'm emphasizing what it means. This is a way of putting sets together to make a related set. So what this means is you're setting, this is specifically the set of x, y, z, such that x is in A comma B, y is in C comma D, and z is in Pac-Man comma Ghost. All right? Fine. So suppose you want to calculate the triple integral of f with respect to the volume. This is called the volume integral. Although this does not calculate volume. I just showed you how to calculate volume by integrating a function. If you want the integral I'm about to write down to calculate volume, you'd have to put the f equal to 1. If we set f equal to 1, the thing I'm about to write down actually calculates volume. This would mean something else. I'll describe in a minute, but here's the, you do the limit as, let's say k goes to infinity, limit as m goes to infinity, limit as n goes to infinity of the sum I equals 1 to k, sum j equals 1 to m, sum n equals 1 to, what have I just done? Oh no. Oh, I should use L for the limit. Sorry about that. Limit as L goes to infinity, LMN. And here I'm going to do I, J, K for summation variables. Sorry about that, guys. I, J, K down here. And the limits are going to be LMN. Sorry, poor planning on my part. Sum over I, J, K, ranging from 1 to L, 1 to M, 1 to N. And then you do f of a sample point, x sub I star, y sub j star, z sub k star, delta x, delta y, delta z. This star is just as a notation for the sample. We're picking a sample point in that ith sub box. So like to calculate this triple integral, we're taking the cube and like chopping it every different which way into a bunch of subcubes. And so we can talk about the ijk subcube. X sub I star, y sub j star, z sub k star is somewhere in that ijk box. I really don't want to write any more because we're never going to actually work problems which require much specificity in this regard. This is just a conceptual backdrop for what we're doing, okay, guys? But there it is. I mean, that would be the triple integral. What does it physically mean, though? I mean, special case. Special case. If we do triple integral over b of dv, what's that? That is the volume of b. That will be the volume of b if you do that integral. Because you're adding up the volume of each little box and taking the sum, right? So that gives you the volume of the whole box. We're going to soon replace this r, which is a rectangle, and the b, which is a box, with things that are curvy. And then it'll be more exciting. Yes?
So the triple integral calculates the volume of the shape underneath the...
Nope, it does not. This triple integral, notice that there's no f. So here's an interpretation. F could, say, be equal to dq dv, for example, the charge per unit volume, right? This is the charge per unit volume. If it was a charge density, a volume charge density, charge per unit volume, then what would the meaning of f dv be? It would be dq, right? So the meaning of this triple integral, it would mean that you're calculating the total charge, for example, over the box, if you were given that F was the charge per unit volume. Not the surface area, no. No surface area here. We're talking about volume density. Another thing, if F was the mass per unit volume, right, just the ordinary density, mass per unit volume, what would the integral of F dV be? Well, it would be the total mass contained in the box. So if we think about F being a density, a volume density, then this integral will calculate the net amount of whatever that density represents, be it mass or charge. You could do the same thing back over here. If, likewise, if F was equal to dq dA, then the integral of F dA over R is actually the integral over R of dq. So that would be the net charge on R, if F had the interpretation of being charge per unit area. So you could talk about charge per unit area, or more generally, you could talk about charge per unit volume. You could talk about charge per unit length for a line. All of these things are covered in Physics 232, right? Well, we may not have experienced that yet, but they're in there. Okay, so my point is, mathematically, the integral is just a nested limit of sums that go on forever and infinitely subdivide either an area or volume, just like the one-dimensional integral does. These are just the natural extensions of the Riemann integral for 2 or 3 variables. I won't even write down the n-dimensional one, but I think you know what to do. If I write this much, if I had n variables, you just take n limits and take your n-dimensional hypercube and chop, 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 almost the same formula. Great. So you remember in Calculus 1 where you calculate bunches of integrals using Riemann sums? Do you remember that? I hope you don't remember that, because if your instructor made you spend a lot of time calculating integrals from Riemann sums, it's really not something that's actually that important going on, is it? How many times have you calculated an integral from a Riemann sum since Calculus 1? I'm being somewhat facetious. It's actually important to understand the mechanics of that, to set up integrals that relate to real-world problems. That's true. I can't take that away. But in terms of calculus, just formulaic calculus that you study in this course, no, you don't ever, we always find antiderivatives and use fundamental theorem of calculus, right? There's something similar that happens here, thankfully. And here's how it goes. So there's something called Fubini's theorem. And Fubini's theorem allows us to trade these monstrous doubly infinite limits and sums that would be quite a drag to actually calculate. And here's how you calculate them. It's really quite beautiful. So for the rectangle that we just looked at, you can do it one of 2 ways. You can integrate from a to b, and then integrate from c to d, f of x, y. So it's inside out. So this goes dy, dx. Or your other choice is you can integrate from c to d, and you can integrate from a to b, and you got yourself f of x, y, dx, dy. So this is a theorem, but that's actually how we always calculate in here. Well, for rectangular regions. So the way it works is you do the inside integral first, and then you proceed to do the outside integral, okay? For 3 variables, so we do the integral from a to b, integral from c to d, integral from Pac-Man to Ghost, f of x, y, z, and I have to pair the differential inside out with the one that comes next. So like, what's Pac-Man and Ghost? That's bounds for what? It's bounds for z, so we put a dz here. You do that integral first. Then next, you do the integral over y, because that's what's paired with d and c. And then finally, you do the integral with respect to x. there's 6 different ways you can set this up. Here's another one. We could also say the integral from Pac-Man to Ghost, integral from A to B, integral from C to D, just to keep it, give you a different order of integration. How would you tell me which differential comes first and which comes last, if you understand the pattern? What we got? We got dy, then dx, then dz, yeah. Let's actually do some calculations then. Let's integrate over the unit square, x squared plus y squared. And often we write dx dy for dA, okay? I've been writing dA, but you can also write, in place of dA, you can also write dx dy. In place of dv, you also can write dx dy dz, okay? Those are common notations. If you don't want to write dx dy dz, you can just write dv. If you don't want to write dx dy, you can just write dA. Yeah? So here it is. So Fubini says I integrate from 0 to 1. I integrate from 0 to 1. X squared plus y squared. And it doesn't matter which one I do first, really. Let's see here. So that's integral from 0 to 1. So the way you do this is you just integrate the middle integration. You integrate with respect to x holding y fixed is how this works, okay? So that's 1/3 x cubed plus xy, right? Evaluated from x equals to 0 to x equals to 1. And then after all that's done, I still have to do what? The y integration, right? Yep.
Is the y supposed to be squared in the second term there?
Oh, it very much should be squared. Sorry about that. Let's see here. So that's the integral from 0 to 1. And what you got, well, this is 1/3. And we get plus y squared, it looks like. Because if you plug in x equal to 1, you get 1/3 plus y squared. And if you plug in 0, you get 0. And I'm using the fundamental theorem of calculus to calculate that integral. Then we integrate with respect to y. We had ourselves a 1/3 y plus 1/3 y cubed. Evaluate that from y equals 0 to y equals 1. I mean, we take the difference at 1 and 0, right? Fundamental theorem of calculus. Part 2 for me. Anyway, so that is 1/3 plus 1/3 minus 0. Minus 0. Anyway, so what you got? You got 2/3. What does this mean geometrically? What did we actually just calculate the volume of? One of our favorite examples, the what? The paraboloid, right? So this is my R. And we just calculated the volume under the paraboloid. So it's like this. Like this. Yeah. I'm not sure what the top looks like. It might be, should be more, does it look like that? I'm not sure what the top looks like. I can't think. No, it should be higher here and lower here, because it goes to height 1. It goes to height 1 on the coordinate axes, right? But it goes to height 2 over this point. This point is 1, 1, right? So that maps to height 2 when you feed it to x squared plus y squared. So it's something like this. So it's basically the shape that's under the paraboloid, right? If you can imagine taking a box right here and connecting up to there, well, it would connect to here really, and then that would kind of like, I can't draw it worth anything, but it's the volume between the box in the xy plane and the paraboloid. That volume is 2/3. All right, let's do it. What if we were asked to integrate, let's see here, integrate, 0, 1, 0, 2, 0, 3 of, let's say, x plus yz. And let's say dx, dy, dz. All right. How do you actually do that? Do it one step at a time, integral from 1 to 0, 0 to 2. My first integration is x, right? So that's 1/2 x squared plus xyz, evaluated from 0 to 3, dy dz. So I think as you start to do these, you start to realize about half the writing I'm doing you don't really need to do. I mean, most of you probably would have been okay. Well, I don't know, you get into trouble though. That's 9/2 plus 3yz dy dz. So I might have been stupid and thought I should have 1/2 instead of 9/2 if I was being careless. I don't know. You gotta be careful. Then I do my y integration. So that's 9/2 y plus 3/2 y squared z, evaluated from y equals to 0 to y equals to 2. Still integrate my z. Integrate from 0 to 1. So let's see here, that's 9. And the other one, 6z. And so what I get 9 plus 6/2, otherwise known as 12. Please don't ask me what this means geometrically. I'd rather not explain. I mean, to understand it in terms of direct geometry is to ask a question about the hypervolume in some four-dimensional space of the graph w equals x plus yz. So we don't think about triple integrals like this directly geometrically. In terms of applications, we think about that. Maybe it's the density, right? X plus yz is the mass per unit volume over the cube 0, 1 to 0 to 2 to 0 to 3. We just calculated the net mass is 12 in that cube, given that weirdo density function. Okay. So I think I could go on doing these, but I bet if I gave you a list of 20 homework problems like this to do, you probably could do them, right? These, what's that? You'd be extremely happy to have, yeah, well, we'll see. Well, we'll see. Actual numbers for answers. Hey, we got pairs of numbers for answers last time, and some numbers, like we had 3/2 and 5/2. I mean, like root 2 is, you say like root 2 is not a number. I mean, we talked about root 2 last time. Root 2 is a number, right? Square root 2? It's a number. I feel like it's a number. It's not a, square root of 2 is not a pretty number. I feel like those are fighting words. Let's see here. If I was a better mathematician, I would be deeply offended. Okay, so next up, curvy regions. So what if you take your rectangle and replace it with something like this? So you go from A to B, all right? But the top is y equals, say, f2 of x, and the bottom is y equals to f1 of x. So at every point x, y, we have the following pair of inequalities. We have A is less than or equal to x is less than or equal to b, and we have that f1 of x is less than or equal to y is less than or equal to f2 of x. These two conditions mean that xy is an element of the region R, okay? No longer a rectangle, right? A curvy region. This kind of region is called type 1. All right. Now, so that's a type 1 region. You can also talk about type 2 regions. Type 2 region looks more like the following. C, D. And then over here, squiggle, 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 squiggle. So here we're looking at x equals to g2 of y. On the other side, we're looking at x equals to g1 of y. And we have the following inequalities met for any point x, y in this region. In particular, c less than or equal to y less than or equal to d. And we also happen to have that g1 of y is less than or equal to x is less than or equal to g2 of y. These pair of inequalities are the necessary ingredients to be counted as an element of the region R. R. All right, this is a type 2 region. There is a Fubini theorem. In fact, that's probably not really the Fubini theorem. The real Fubini theorem, those are the weak forms of the Fubini theorem that I wrote down over there. I think what I'm about to write is probably best called the strong form of the Fubini theorem. And the strong form of the Fubini theorem simply says this: if you wish to calculate the integral over such a region R of a yet, let's call the function g this time, g dA, well, you can calculate it as the integral from a to b, the integral from f1 of x to f2 of x, g of x comma y. And then remember that the bounds get paired inside out. So the f1, f2 bounds go with dy. These describe the bounds for y. That's why this is paired with dy. And then, finally, you integrate over x. This is a type 1 integration. Also, we have a corresponding theorem for type 2 regions. Integrate from c to d, integrate from g1 of y to g2 of y, g of xy. This time we must do dx first, and then dy first. Okay. Type 1, you got type 2. There are regions which are both type 1 and type 2 at the same time. Do you know any such regions? For example, the rectangle, right? It's both type 1 and type 2. And by the way, I just wrote down up here that which one of these would be type 1, which one of these would be type 2, the setup. Going back to my calculation, which one's type 1, which one's type 2. So this is, type 1 setup. Over here is type 2 setup. There's a theorem. If you have a region in the plane which is simultaneously type 1 and type 2, it doesn't matter which way you calculate, you're going to get the same answer. These are just different ways of dividing up that infinite summation. Okay? There is a corresponding sort of idea for triple integrals for, regions which are not cubical, regions bounded by graphs, and we'll talk about that, but I think I should do an example of the type 1, type 2 before we get to that. I'll probably talk about the more complicated triple integral idea tomorrow. So here's an example. Let's let f of xy equal to x times y, right? And let r equal to x comma y, such that 0 less than or equal to x less than or equal to 1, and minus x less than or equal to y less than or equal to x. So could you picture this region? What's it look like? Like y equals x is the top, y equals minus x is the bottom. It goes from 0 to 1. This is the region. So if we want to calculate the integral of f dA over this region, we're supposed to do what? Integrate from 0 to 1, integrate from minus x up to x of x, y, which comes first, dy or dx now? Yeah, the dy. Dx. Let's see here. So integrate with respect to y, I get 1/2 xy squared. I have to evaluate that from y equals minus x. You know, that's my lower bound, my upper bound is y equals x. Remember fundamental theorem of calculus, take the difference of those. So I've got integration from 0 to 1 of 1/2 x cubed minus 1/2 x cubed. What do you know? Not especially surprising if you think about the problem I set up, right? Do you see why that should be 0? If you think about it in terms of symmetry, look at the function xy, right? Look at the region. What's the nature of this region here? Up here, you've got y greater than 0. Down here, you've got y less than 0. Those regions are symmetrically situated. X is the same for both of them, right? And the thing we're integrating is also symmetric with respect to, you know, and it's just, it makes sense that that integration should work out to 0 because the top half should give like a positive answer and the lower half should give a negative answer, right? And they should cancel out, basically. What would happen if we just take the top half of it? What if we you know, said t was just this piece? How would that change this calculation? Yeah, the 1/2 y squared would have gone from 0 up to x instead of minus x to. So basically this would have 0 less than or equal to y less than or equal to x, 0 less than or equal to x less than or equal to 1. Those inequalities describe the integration region T, and so that's how the integration would work out. And when we actually do that, we just get the integral from 0 to 1 of 1/2 x cubed dx, which integrates to 1/8. So yeah, the top part of R gave us 1/8. The bottom part actually gave us minus 1/8 if you work it out. There's a popular example to show you guys at this point, if I could find it. All right, this is not going to go well. I'm going to butcher this example. There's about a 50% chance it's going to be wrong, what I'm about to do. But I'm going to try. I'm going to try. I'm trying. My heart is in the right place, even if the calculations are wrong. So the region I want to look at, I think, is this. All right, so it's actually the one we just looked at. It's T again. All right? And I want to look at the integration over T of, goodness gracious, I think it's e to the x squared, you know, dx dy. you may recall e to the x squared is something we do not know how to integrate. Right? So while it is true that this region T is both type 1 and type 2, it is also true that only one of those choices will actually allow you a calculation that you can do, assuming I set it up right. Let's see. So which should we do? I think we should try this. The integration from 0 to 1, integration from 0 to x, right, of e to the x squared dy dx, right? So let's use a type 1 setup. Why is this great? Because the first integration is not with respect to x, right? So, yay, we can do that. So we got ourselves a y e to the x squared evaluated from y equals to 0 to, well, y equals to x, which gives us the integral from 0 to 1 of x e to the x squared dx. Now, there is hope, because this is a mere u substitution. Such a simple u substitution that we can do it up in here in our noggin. This is 1/2 e to the x squared. That's the antiderivative evaluated from 0 to 1. So the answer is 1/2 e minus 1. There you go. Make u equals x squared if you're rusty, right? That's why we did that. That half is there because it's a u substitution. This is a pretty popular homework question. If necessary, change the type of integration so that the integration is possible. So how do you change a type 1 to a type 2? What if I had set this up as a, now it's pointless to do for this one, but what would this have been as a type 2? We have to think about it, right? 0 less than or equal to y less than or equal to 1, because y equals 0 is down here, right? And this is y equals 1 up here, right? And what do we have for x? We have y is less than or equal to x is less than or equal to 1. So the type 2 integration would have been integration from 0 to 1, integration from y up to 1 of e to the x squared dx dy. Again, I'm not interested in that integration because I can't do the initial iterated integral. By the way, these integrals I'm teaching you, this is iterated integration. You do one at a time, then the next iteration. So like that's the setup for type 2, but it's a non-starter, right? So type 1 was the way to go anyway. But another popular homework question is like change a given type 1 to type 2 or vice versa. How do you do that? Well, you actually have to draw the picture and think through it. It's all of your worst fears, really. Sorry. Sorry. Well, drawing pictures and figuring out inequalities is much more complicated than actually doing integration or differentiation, right? It's a far more complicated thing. Students will always tell me in about a week, I understand integration. I really understand it. I just don't understand the bounds. Yes, the bounds are the only thing here which people struggle with. So if you're struggling with bounds, good. That's the thing you must struggle with. You must conquer how to settle the bounds. The actual integration, iterated integration, we could train monkeys to do that. It's not a hard thing, It's the setting up the bounds. Well, I mean, come on. What? You got something against monkeys? No?